Hello, today's topic of discussion is first order linear differential equations. In this chapter, we have two modules. In module 1, we have started with the basic definition of first order linear differential equations along with the discussion on homogeneous and non-homogeneous linear differential equations, the integrating factor and the exact equations. In module 2, we will discuss about the existence and uniqueness property of the first order linear differential equation. So, let us start with the basic definition along with some examples of linear differential equations. In this module, our focus of study will be the first order differential equation of the form dx dt is equal to f tx, t belongs to some interval a b. Our aim is to search for all suitable functions x t where t belongs to the interval I a b such that its first order derivative exists on a b, and for given function f it satisfies the equation 1. Thus, a solution of the differential equation given by 1 is said to be a general solution of 1 if all other solutions of the differential equation can be obtained from this solution. Let us consider the example dx dt plus 2x equal to e to the power t. It can be easily verified that x t equal to c1 e to the power minus 2t plus 1 by 3 e to the power t, which is given by equation 3 and c1 is an arbitrary constant, satisfies the differential equation 2 for all t belongs to R. That is, equation 3 is a solution of equation 2. Also observe that all other solutions of 2 can be obtained by assigning suitable values to the integral constant c1. So, we call the expression 3 as the general solution of the given differential equation 2. Geometrically, for each fixed value of c, the equation 3 represents a curve in the tx plane, and the totality of these curves is known as the integral curves of 2. In several cases, we are not interested in all the solutions, but only in a particular solution satisfying a given initial condition of the form x t 0 equal to x 0 given by equation 4. To be more precise, we can define the solution of 1 with initial condition 4 as given in the following definition. A real valued function x t defined on I is said to be a solution of the initial value problem 1 with initial condition 4 on I if the following condition holds. Number 1, x dash t exists for all t belongs to I. Number 2, x t 0 equal to x 0 where t 0 belongs to the interval I. The points t x t belongs to I cross R and x dash t equal to f where t belongs to I. Solving nonlinear differential equation is a lot more difficult problem than solving the linear ones, as there are several methods available to solve linear differential equation, but no general methods available so far to solve nonlinear equations. Therefore, the concept of approximate solutions are quite useful in the case of nonlinear differential equation. Also, the concept of general solution may differ from general solution of linear differential equation. In particular, nonlinear differential equation may have some special solution known as singular solution that cannot be obtained by the general solution of the nonlinear differential equation. To handle any problem, we will try to relate it to some other problem which is either solved or comparatively easy to solve. Now, if we assume that we know only a little calculus, then we can solve only a few differential equations of first order. Consider the simplest differential equation dx dt equal to 0. By elementary calculus, we know that the only solution of the above differential equation is a constant function, that is x t equal to c, where c is the integrating constant. Consider another differential equation of the form dx dt equal to f t, where f is any integrable function of the time t. Now, to solve the differential equation 6, we simply integrate both sides with respect to t, and we get x t equal to integration f t dt plus c, where c is an arbitrary constant to be determined with the help of initial condition. Once we know the method of finding solutions for differential equation 5 and 6, we have any other differential equation of first order, we will somehow try to find a function g and rewrite the differential equation in the form d dt of g t x equal to 0, or in the form d dt of g t x equal to some function of t, say h t. As we can see, in most of the cases this may not be possible to do so. Hence, we may not be able to solve many differential equations. The definition of the general first order linear differential equation is an equation of the form dx dt plus atx equal to bt, given by equation 8, where at and bt are continuous function defined on an interval I. If we rewrite it in the form 1, then gtx is equal to minus atx plus bt. When bt equal to 0 for all t belongs to I, then 8 is called a homogeneous differential equation, which is of the form dx dt plus atx equal to 0, given by equation 9. Otherwise, when the function bt is not identically 0 on I, then we call 8 as a non-homogeneous equation. Also, for non-homogeneous problem, the function gtx is equal to minus atx is linear in x, that is g of t comma c1 x1 plus c2 x2 is equal to c1 gt x1 plus c2 gt x2, where c1 and c2 are any two constants. To solve the first order linear homogeneous equation given by 9, we rewrite it in the form 1 by x dx dt equal to minus at, and we observe that 1 by x dx dt is equivalent to d dt of ln x t, where ln means log to the base e, and this implies d dt of ln of mod x is equal to minus at, and which is nothing but as represented by equation number 6. If we solve this, we will be getting mod x t is equal to c e to the power minus integration a t dt, or mod of x e to the power integration a t dt is equal to c. Since x t e to the power integration a t dt is a continuous function of t and its absolute value is constant, recall that if the absolute value of a continuous function g t is constant function, then g itself must be a constant function, and therefore, x t e to the power integration a t dt equal to c, which implies x t is equal to c e to the power minus integration a t dt. Equation 12 is said to be the general solution of the homogeneous equation 9. In application, usually we are not much interested in the general solution of 9, so we may find the value of the constant c in 12 with the help of the given condition x t 0 equal to x 0. Therefore, the homogeneous initial value problem dx dt plus atx equal to 0 with a given initial condition x t 0 equal to x 0 has a solution of the form x t equal to x 0 e to the power minus integration from t 0 to t a s ds, given by equation number 13. Once we know the solution of the homogeneous problem 9, we want to discuss the non-homogeneous equation dx dt plus atx is equal to bt. Again, using the same working method, we rewrite the non-homogeneous equation 14 in the form ddt of some mu Tx is equal to Bt, where mu Tx is a suitable function such that ddt of mu Tx is equal to x dash plus At into x. And then to integrate both sides for the function mu Tx. From equation 16, we have del mu del t plus del mu del x dx dt is equal to dx dt plus At into x, which is nothing but a first order partial differential equation, solution of which is supposed to be a relatively difficult problem than solving an ordinary differential equation. So, at this point it is difficult to check that the expression dx dt plus At into x represents the derivative of some simple expression. The next thing we may ask, that can we make the left hand side of the equation to be of the form ddt of mu t into x, or can we choose a function mu such that the left hand side of equation 14 can be represented in the form mu t into dx dt plus Atx is equal to mu t Bt. Since ddt of mu Tx is equal to mu t into dx dt plus d mu dt into x is equal to mu dx dt plus At mu t into x, it implies that d mu dt is equal to At mu t. Equation 19 is a first order linear homogeneous equation, and by 12 we know how we can solve equation 19. Since we only want such function mu t, we can choose mu t equal to e to the power integration A t dt by taking the constant value c equal to 1. For this value of mu t, then 14 becomes ddt of mu t into x is equal to mu t into Bt. By integrating both sides from t0 to t, we get x t equal to 1 by mu t multiplied by mu t0 into x0 plus integration t0 to t mu s bs ds, given by equation 21, where mu t is given by equation 20. The function mu t is equal to e to the power At dt is called an integrating factor for the non-homogeneous equation 14, since after multiplying both sides by mu t, we can immediately integrate the equation 14 to find all its solution. Please note, given a differential equation, you need to find a function mu t, so that if you multiply that function to both sides of the differential equation, you will be able to solve, and that particular function is called the integrating factor of the differential equation. We consider the example dx dt minus 2 Tx equal to t with initial condition x0 equal to 0. By comparing this with the non-homogeneous equation 14, we can see that the function At is equal to minus 2t, and therefore, the integrating factor will be given by mu t is equal to e to the power integration minus 2t dt. And if you integrate this simple function, you will get the integrating factor to be e to the power minus t square. We next multiply this integrating factor to both sides of equation 23, and if you do that, you will get equation 25, which is e to the power minus t square multiplied by dx dt minus 2 Tx is equal to t into e to the power minus t square. The left hand side can be put in the form d dt of e to the power minus t square x is equal to t e to the power minus t square. Now, if you integrate this from 0 to t, you will get the solution as x t equal to minus half plus c e to the power t square, where c is the integrating constant. And for a particular solution of this initial value problem, we will get x t equal to half of e to the power t square minus 1. Thus, the solution procedure for solving the homogeneous problem presented in the last slide suggested us to solve the more general equation of the form dx dt equal to gt divided by fx, where gt and fx are continuous functions. This equation and any other equation which can be put in the form given by equation 27 is said to be separable. Please note equation number 27. Here it is a function of t and x, where t is an independent variable and x is a dependent variable. If you can separate both the independent variable and the dependent variable, then this particular differential equation is called to be separable, and hence separating the variables and integrating 27, we will have equation number 28, which is integration fx dx is equal to integration gt dt. In addition to equation 27, if we impose an initial condition on x as x t 0 equal to x 0, then we may directly integrate 28 between t 0 to t. So far, we have discussed the definition of the first order linear differential equation along with some examples. We have also seen the homogeneous and non-homogeneous differential equations and how they need to be solved with respect to first order only. Our next topic of discussion will be the exact first order differential equation and the non-exact first order linear differential equation, and how we solve the non-exact first order linear differential equation with the help of the integrating factor. We now discuss about exact first order linear differential equations. As discussed in example 0.1, we can solve all the differential equation of the form which can be put of the form d dt of g t x is equal to 0, given by equation 29, or of the form d dt of g t x equal to h t, given by equation 30 for some function g. Equation 30 can be thought as a special case of 29, as 30 may be written as d dt of some g bar t x equal to 0 with g bar t x is equal to g t x minus integration h t dt, which is of the form equation number 29. So, without any loss of generality, we will focus on equation 29. Equation 29 can be solved by integrating both sides to obtain the solution given in implicit form g t x equal to c. To obtain the explicit form, we may then solve g t x equal to c for x t. This will be more clear if we consider the example number 0.4. Let us take a differential equation of the form 2t sin x plus x cube e to the power t plus t square cos x plus 3x square e to the power t dx dt equal to 0. To see if this differential equation is exact or not, we have to put the left hand side in the form of d dt of some function which is equal to 0. And if we see we will find the function to be t square sin x plus x cube e to the power t, because if you differentiate d dt of t square sin x plus x cube e to the power t, you will get this to be 2t sin x plus x cube e to the power t plus t square cos x plus 3x square e to the power t dx dt equal to 0, which is actually the expression for the differential equation of the given problem. Hence, the solution of the given differential equation is t square sin x plus x cube e to the power t equal to c, where c is the integrating constant. As pointed out in the previous example, that is 0.4, that if we know a given differential equation is of the form 29, then we can simply integrate the differential equation and get GTX equal to C as its solution. At this point, we may ask a very important question, that how do we know that a given differential equation which is of the form 29 actually can be written in the form 29, as it is not easy to visualize that 2t sin x plus x cube e to the power t plus t square cos x plus 3x square e to the power t dx dt is actually equal to d dt of t square sin x plus x cube e to the power t. So, to identify the set of differential equation which actually can be put in the form, we observe that d dt of g of t x t is equal to del g del t plus del g del x into dx dt. Hence, any differential equation m t x dt plus n t x dx is equal to 0 can be written of the form 29 if and only if there exists a function g t x such that m is equal to del g del t and n is equal to del g del x. In this case, the differential equation m dt plus n dx equal to 0 is equivalent to d dt of g t x equal to 0, and we call the expression m t x dt plus n t x dx is in exact differential form, and hence equation 31 is called an exact differential equation. So, given two functions m t x and n t x, we want to find a function g t x such that equation number 32 holds. So, let us try to find out for what kind of functions m t x and n t x we get a function g t x which will exist. So, overall a exact differential equation will be of the form m t x dt plus n t x dx equal to 0 if you can express it in the form d dt of some function is equal to 0. If we recall the basic calculus, we will see that the mixed second order partial derivative of a function g are equal, that is del to g del t del x is equal to del to g del x del t, which is given by equation 33, and here we have to assume that the function g is smooth enough so that the both side exists and are continuous. From equation 31 we have del m del x is equal to del n del t. So, condition 34 is the necessary condition for the differential equation 31 to be an exact differential equation. The following result is put in the form of a theorem which tell us that the condition 34 is also a sufficient condition for equation 31 to be exact, and hence the condition 34 is known as the exactness condition for the differential equation 31. Let us put all these results in the form of a theorem which says that let m t x and n t x be continuous and have continuous partial derivatives with respect to t and x in a rectangle R, which is T x such that t lies between a and b and x lies between c and d, then there exists a function g which is a function of t and x such that m is equal to del g del t and n is equal to del g del x if and only if del m del x is equal to del n del t. For the proof, we start with the function m which is equal to del g del t, and this implies if we integrate both sides, g t x is equal to integration m t x dt plus alpha x. Please note this alpha x will only be a function of x because we are integrating both sides with respect to t. Since n t x is equal to del g del x, so again differentiating the above expression of g with respect to x, we will get del g del x is equal to integration del m del x dt plus alpha dash x, which implies we replace del g del x by n, which is equal to integration del m del x dt plus alpha dash x, which implies alpha dash x is equal to n minus integration del x of m dt, given by equation number 36. Now, a function of x alone cannot be equal to a function of both t and x, and thus this equation 36 will hold good if the right hand side is a function of x alone. Please note that the left hand side is only a function of x and the right hand side is a function of t and x, and hence we will have del del t of alpha dash x is equal to 0. And if you do that, you will be getting del del t of n minus integration del m del x into t equal to 0, which implies del n del t minus del m del x is equal to 0, and which implies del n del t is equal to del m del x, which is our required condition. Suppose del n del t is not equal to del m del x, then there is no function g such that del g del t equal to m and del g del t is equal to n. But if the condition del n del x equal to del m del x holds, then alpha x is equal to integration of n minus integration del m del x dt multiplied by d of y. Consequently, m equal to del g del t and n equal to del g del x, with g is equal to integration of m dt plus integration of n minus integration del m del x dt. Hence, our remark, the differential equation dx dt equal to f can always be written in the form m plus n dx dt equal to 0 by setting m equal to minus f and n equal to 1. Let us consider the differential equation m plus n dx dt equal to 0, which is not exact, that is del m del x is not equal to del n del t. Now, the question is how to make it an exact differential equation, or in particular can we find a function mu such that the differential equation becomes exact. So, the answer is in the affirmative, provided the function mu can be written in the form del del x of mu m is equal to del del t of mu n. That is m del mu del x plus mu del m del x is equal to n del mu del t plus mu del n del t, given by equation 42. Thus, the equation m plus n dx dt equal to 0 is exact if and only if mu satisfies 42, and then mu is known as the integrating factor. Unfortunately, there are not many forms of mu for which an explicit solution of 42 is given. So, we consider two simple cases. In case 1, we take mu Tx as a function of t only, that is mu t, which implies d mu dt is equal to del m del x minus del n del t divided by n multiplies by mu, which implies mu will be exponential of RT, where RT is given by del m del x minus del n del t divided by n. And in case 2, we can take mu x t as a function of x only, which is given by mu x, and which implies d mu dt is equal to del n del t minus del m del x divided by m multiplied by mu, which implies that mu x is exponential of some function s x, where s x is equal to del n del t minus del m del x divided by n. You may see that in both the cases, the expression del n del t minus del m del x by n is used to find the integrating factor. In most of the cases, the above function is a function of both t and x. Only for very special pair of functions m and n, it is a function of t or x alone. Therefore, in most of the cases, we will not be able to solve the differential equation analytically, and we may have to take the numerical methods to solve the differential equation. Summing up module 1, we have started with the basic definition of first order linear differential equation. We have also looked into the solution of homogeneous and non-homogeneous first order linear differential equation. We also find the solution of exact and non-exact first order linear differential equations. In module 2, we will learn about the uniqueness and existence property of the first order linear differential equations. Thank you.